Welcome to Component 24, Healthcare Data Analytics, Unit 1, Introduction to Healthcare Data Analytics. This is Lecture B. This unit introduces the basics of working with healthcare data for the novice. The different types of data are explored, as well as the array of technology and tools available for working with data. Big data is defined, and the special challenges related to working with data are discussed. The objectives for this unit, Introduction to Healthcare Data Analytics, Lecture B, are to categorize data into the different types, define or apply common terms used in data analysis such as sample, paired, histogram, population, correlation versus causation, descriptive, etc. Determine whether data fits the definition of big data, and summarize the challenges faced when working with big data. Before we go any further into data analytics, let's review the concepts of data, information, and knowledge. Let's look at this from the bottom up, because everything depends on the bottom data layer. As a reminder, data are simple symbols, isolated facts, and measurements. When such data are processed, put into a context, and combined within a structure, information emerges, and that is shown on the second layer. Information provides the answers to who, what, when, and where. When information is given meaning by interpreting it, information becomes knowledge. Knowledge answers the how questions. Finally, wisdom, at the very top of the pyramid, answers the why questions. Now we will look at aspects of the data layer. The data layer of the DIKW hierarchy contains many types of data: laboratory results, X-rays, blood pressure data, physician's notes, and so on. Data in an EHR or other health information system, such as a laboratory information system or radiology information system, can generally fall into one of three categories. Quantitative data includes numbers, such as a laboratory glucose result of 130, a patient date of birth, or a blood pressure of 130/70. Qualitative data includes narrative text, such as physician's notes, as well as demographic data, such as race, ethnicity, and religion. A third type of data includes transactional data, such as date and timestamps of when medications were delivered. We can also look at data in another way, as shown on the next few slides. Data come in many forms, and those forms determine what can and cannot be done with the data. For example, two patient names cannot be added together. It makes no sense to try to add the names John Doe and Maria Garcia together, or to try to add the data point eye color is blue from one patient to the data point eye color is brown from another patient. However, it can be very important to be able to graph a child's height over time or to compare a patient's kidney function tests against their medications. The forms that data can be categorized into are referred to as scales of measure, and there are 4 scales: nominal, ordinal, interval, and ratio. We will explore these on the next few slides. The first scale of measure is called nominal data. Dictionary.com defines nominal as a discrete classification of data in which data are neither measured nor ordered, but subjects are merely allocated to distinct categories. That is, they are named. So, data that are considered nominal are names, labels, and categories. For example, patient first, middle, and last names, such as John Doe and Maria Garcia, would be considered nominal data. Other examples would be data labels or categories, such as patient gender, eye color, religious preference, or drug names. In general, nominal data aren't used in statistical analysis other than as labels. You can count the number of patients with the same last name, but it makes no sense to try to subtract a John Doe from a Maria Garcia. Note that the ordinal level includes the properties of the nominal level, so all ordinal data also have a name. Now let's say that we were able to measure Marcus, Amber, and Hans's heights in inches. 1 inch is exactly the same, regardless of whether it is for Marcus or for Amber. So we can compute exactly the size of the differences between the 3 children. In other words, we can calculate and compare the intervals. Data that fall into either interval or ratio classification have all the properties of both nominal and ordinal data. That is, these data have a name, such as Amber's height in inches, and they also have some sort of order or ranking, tallest, shortest, middle. But what sets interval and ratio data apart is that with these kinds of data, we can determine and compare the size of the difference between 2 data points, because each interval, such as an inch or a degree, is the same size. 1 inch for Marcus is exactly the same distance as 1 inch for Amber. Note that the distinction between interval and ratio is that ratio data have an absolute 0 point. In many cases, this distinction is not made, and interval and ratio data are simply grouped together into a category referred to as scale data. The Health Information Management Association, AHIMA, pronounced AHIMA, identifies several types of inconsistencies and quality issues that can occur when data are captured and stored. These include inconsistent naming conventions, such as systolic blood pressure versus blood pressure systolic. Inconsistent definitions, such as how the date of admission is defined across departments. Varying field lengths for the same data element, such as one system allowing a patient's name to be up to 50 characters, while another system allows 25 characters. Varied data elements, such as male, female, or you for patient gender in one system, while another system uses 1, 2, or 9, or male, female, or unknown. AHIMA further states that inconsistencies in data definitions can lead to inaccurate data use and health data reporting and can potentially affect the quality of care. An essential part of any data analysis is developing a correct understanding of the data you are working with. Take a look at this simple synthetic data set. Look at the columns for smoke and for weight. Both are given in numbers. So shouldn't that mean that both could be analyzed using numeric methods? No. The values in the smoke column are referring to categories of smoking status. The only way you would know that is to obtain the data dictionary that the researcher developed to explain each field. Obtaining the data dictionary is an essential first step in understanding the data you are working with. A data dictionary is defined by the Health Information Management Systems Society, or HIMSS, as a standard definition of data elements. It ensures that all necessary data points are accounted for and reported correctly. It should include specific descriptions of the data element from the report requirements, an associated business or clinical process, and information from the underlying database. Documenting the source of the data, process and database storage, creates transparency to the organization and enables analysts to report consistently and accurately. If a single data element has multiple sources, e.g. both a billed CPT code and a service documented in the EMR, a data dictionary ensures that all elements being measured are considered correctly. This documentation process also helps to discover if the necessary data elements are even available to the organization. Here is an example data dictionary for a few meaningful use measures. Here is part of the data dictionary for the smoking versus weight example on the earlier slide. Here you can see what each number under smoking status means. For example, a 1 indicates that this patient currently smokes every day. In addition, each of these values is linked to a specific SNOMED CPT code. Now let's discuss some common terms that are used in data analysis. If you have had any statistics coursework, this should be a refresher for you. Some of the terms include population, sample, dataset, paired, descriptive statistics, frequency table, histogram, chi-square, t-test, and correlation versus causation. First, let's look at the concept of a population. Normally, we think of population as the people living in a certain area. The term population, as it's used in statistics, is a group of things that have something in common. While a population does not always have to mean people, it often does. Common examples of populations in healthcare analytics would be all the patients in a hospital, patients with a certain diagnosis, patients with a particular attribute such as gender, smoking status, or age group, or everyone who had a certain surgical procedure in a given year and who were operated on by a specific surgeon. The next term we'll look at is sample. Let's say you wanted to find out the average weight of babies born in the United States in 2015. That would be the population you would be studying. It would be very difficult, if not impossible, to get the weight for every baby. Instead, you would get weights from a representative portion of the population and then extrapolate the average weight of all babies. This portion or subset is called a sample. Statisticians use a variety of techniques to determine that the sample is representative of the entire population and to determine how big the sample size should be. In this case, how many babies' weights need to be obtained in order to accurately derive the average weight. Paired samples are also used. In this case, the samples are matched, such as the same patient before and after a treatment, or patients with similar characteristics such as age, gender, and diagnosis. Now let's think about the study of babies' weights at birth. We decided that we could not measure the weight of every baby born in the United States in a given year, so we decided to take a representative sample, perhaps weighing every baby in a specific hospital for a period of time. The purpose of sample or subset is because it is often impossible for various reasons to include every patient in a study. What we want to know is how well does our sample approximate the entire population of babies born in the United States? This is where the confidence interval comes in. It provides a range of values that is likely to contain the population parameter of interest, in this case baby weights. Confidence intervals are constructed at a confidence level, such as 95%, selected by the user. What does this mean? It means that if the same population is sampled on numerous occasions and interval estimates are made on each occasion, the resulting intervals would bracket the true population parameter in approximately 95% of the cases. What are confidence intervals can be found in NIST SE MATECH E-Handbook of Statistical Methods, whose URL is provided at the end of the slides. A data set is a collection of data for a specific purpose. For this presentation, for example, the data set is a collection of 500 records that consists of age, gender, state of residence, marital status, blood type, weight, eye color, and smoking status. Descriptive statistics give basic statistics of numeric data and should be one of the first analyses run on a data set. Descriptive statistics can identify some errors. For example, does the count of the number of records, 500, match what was expected? Do the minimum and maximum values look reasonable for a range of patient weights? Does the mean, the average, look reasonable? Two important concepts in statistics and analytics are correlation and causation. Correlation is the relationship between two things. In statistical analysis, it is a measurement of the relationship between two variables. Causation is that one thing causes another thing. For example, we know that the measles virus causes measles disease, and smoking causes certain types of lung cancers. However, an important concept to remember is that just because there might be a statistical correlation between two things does not mean that one causes the other. For example, there might be a statistical correlation between patients with a particular eye color and a certain disease. However, the eye color is not the cause of the disease. Murdoch and Detsky, in a paper published in 2013 in the Journal of the American Medical Association, described 4 ways in which big data may advance healthcare. First, big data may greatly expand the capacity to generate new knowledge. Schneewis, in an article published in the New England Journal of Medicine in 2014, elaborates on this point by describing this new knowledge as the effectiveness of treatments as well as the prediction of outcomes. Murdoch continues by stating, second, big data may help with knowledge dissemination. Third, big data may help translate personalized medicine initiatives into clinical practice by offering the opportunity to use analytical capabilities that can integrate systems biology, e.g. genomics, with EHR data. Fourth, big data may allow for a transformation of healthcare by delivering information directly to patients, empowering them to play a more active role. So what exactly is big data? In September 2015, the National Institute of Standards, NIST, published a document defining many terms related to big data, analytics, and data science. In this document, NIST stated, big data and data science are being used as buzzwords and are composites of many concepts. According to the NIST, big data refers to the inability of traditional data architectures to efficiently handle the new data sets. Characteristics of big data that force new architectures are volume, i.e. the size of the data set, variety, i.e. data from multiple repositories, domains, or types, velocity, i.e. the rate of flow, and variability, i.e. the change in other characteristics. These characteristics, volume, variety, velocity, and variability, are known colloquially as the V's of big data. Big data consists of extensive data sets, primarily in the characteristics of volume, variety, velocity, and/or variability, that require a scalable architecture for efficient storage, manipulation, and analysis. Analysis of big data requires tools beyond standard SQL-based relational databases. Some common tools include Hadoop and MongoDB. According to SAS, Hadoop is an open-source software framework for storing data and running applications on clusters of commodity hardware. It provides massive storage for any kind of data, enormous processing power, and the ability to handle virtually limitless concurrent tasks or jobs. It does this by concurrently processing large amounts of data using multiple low-cost computers for fast results. MongoDB is a NoSQL database that stores data using a flexible document data model that is similar to JSON. Documents contain one or more fields, including arrays, binary data, and subdocuments. Fields can vary from document to document. As we come to the end of this unit, recall when we talked about learning healthcare systems earlier. Schneewis identifies several requirements for analytics in learning systems. First, there needs to be a way to ensure that all patient groups being compared are truly similar. We need automated tools for analysis, as well as the ability to rapidly run automated tools against new data. There needs to be software that can be used with little training and helps prevent errors in interpretation. And finally, the results need to be easily understood. According to the National Institutes of Health, or NIH, biomedical big data faces many challenges. The unwieldy amount of information, lack of organization and access to data and tools, and insufficient training in data science methods make it difficult for big data's full power to be harnessed. This concludes Lecture B of Component 24, Healthcare and Data Analytics, Unit 1, Introduction to Healthcare Data Analytics. In summary, data come in many forms, and those forms determine what can or cannot be done with the data. Big data has the potential to advance healthcare. Analysis of big data requires tools like Hadoop and MongoDB. However, biomedical big data faces many challenges. This concludes Unit 1, Introduction to Healthcare Data Analytics. This introductory unit introduced the concept of data analytics. We covered different types of data and technologies and tools used for working with different types of data. We discussed big data, its characteristics, and challenges faced working with big data. We also discussed common terms used in data analysis. This concludes Unit 1, Introduction to Healthcare Data Analytics. This introductory unit introduced the concept of data analytics. We covered different types of data and technologies and tools used for working with different data types. We discussed big data, its characteristics, and challenges faced when working with big data. We also discussed common terms used in data analysis.